Okay, so welcome back to section 10.2. In section 10.2, we're going to continue building on what we did in section 10.1. In 10.1, we asked the question, statistically, is there enough evidence to support a linear regression for data? So if someone gave us data, we ran a test, we set up our hypotheses, we ran the test, we said, hey, does the evidence support a positive or a negative, a non-zero population linear correlation? And if the answer to that was yes, that the data supports it, then the next question we should ask is, what's the equation of that line? So in this section, that's what we're going to look at. We're going to look at how to find the equation of that line that best fits the point for that data. Okay? That line is called a regression line, or a linear regression line, or the line of best fit, or the regression equation. There's lots of different names that it is given. Okay? We're also going to talk about what marginal change is, what influential points are, and we'll talk just a very little bit about residual plots. Okay? So first off, regression line. If someone has given you that paired data, that bivariate data, the regression line or the line of best fit or least squared line is the line that best fits that data. Okay? When we get that regression line, the algebra of it is going to be called the regression equation. Now here's where things get frustrating, because we're finding the equation of a line, and y'all have been through an algebra course at some point where you were taught this: y equals mx plus b. And you were taught that m here, that stands for the slope of the line, and that the b here, that stands for the y-intercept. Right? And you use that probably dozens, if not hundreds of times throughout your algebra sequences. But suddenly, because this is a stats class, we've got to mess things up. And we've got to say, no, we're fancy, we're stats. So the regression equation is now going to be this monster. We're going to say that y hat equals b sub 0 plus b sub 1x. Well, first things first, y hat is just y from the equation. And did you notice that these two were switched? The x term is normally written first, and the constant term is normally written second. And then, to make things even harder, we swapped out m and replaced it with b1 for our slope. And we swapped out plain old b and replaced it with b sub 0 for our y-intercept. Why did they do this? I have no clue. But I do know that for whatever reason, math writes it like this, but stats writes it like that, where we have, instead of a y, we have a y hat, a predicted value, a response variable, and we have a b sub 0 for our vertical intercept, our y-intercept. We have a b sub 1 for our slope, and then we have an x, not with a hat on it, but just a plain old x. Right? Now, we often call the x the explanatory variable or the predictor variable, and we call the y the response variable. Now, you will hear some people still referring to them as independent and dependent also. But a lot of times, because it's stats and because stats needs to be special, we call it the explanatory variable and the response variable. And we change the order that we write them. We write the y-intercept first, and then we write the x term that has the slope attached to it, and we swapped out m's for b sub 1s, and we swapped out plain old b's for b sub 0s. Right? There's a little bit of reason for this. If you go deeper in the stats and you do this idea of regression on higher power equations, you can get things that look like this. B sub 0 plus B sub 1x plus B sub 2x squared plus B sub 3x cubed. And so I get it, there's logic to this pattern, but for most of my students, they've been trained this way for so long that switching to the stats way of doing things, it's just jarring, okay? But that's okay, we'll get through this, all right? Our objective in this section is to find the equation of the regression line. Now, because the objective is to find the equation of the regression line, we are going to assume that we have reason to do this, that we have run the hypothesis test, and the hypothesis test has told us that the data supports finding this relationship, finding this regression line. Right? All right, just some more notation. Because our work is done on samples, the B sub 0 and the B sub 1 are referred to as sample statistics, the y-intercept and the slope. The population parameter that correlates with these is beta sub 0 and beta sub 1. Okay? When we're working with a sample regression equation, we've got a y hat there. When we're working with population, then we just call it plain old y. Do you see how these are the same structure? Constant plus slope times x, constant plus slope times x. All we're doing is we're over here, because it's sample stuff, we're using the sample statistics for our intercept and our slope. And then over here, because it's a population, we're using the population parameters for our y-intercept and our slope. Okay? We're going to find these, and then the argument is that if we've done everything correctly, they should model that really, really well. Right? All right. Requirements to make this happen is same as the requirements for running the hypothesis test. You got to have that sample data be a random sample. We should see that straight line pattern when we visually. Outliers should be adjusted for, and 2 and 3 are just an attempt to reduce it. Okay? If we were actually doing this using all of the formal steps, we would show that x and y have a normal distribution. Okay? We would show that the corresponding y values for every fixed value of x have the same standard deviation. Right? And that for different values of x, the corresponding y values all lie along a straight line. Okay? Now, we're never going to worry about this at this level. That's a much higher level stats thing. For us, we're worried about this up here. We're worried about, is our data random? Does it look like we should be using a line? And if there are outliers, we should check and see if there may be an error, because they can really affect the outcome. Right? Now, the math behind the scenes, what's happening behind the scenes when the B sub 1, our slope, and the B sub 0, our y-intercept, are being calculated, is we're doing this. Now, hopefully, this still is fresh in your memory. That's that R from the last session. So that R that makes this formula right here look really simple, R times the standard deviation of the y values divided by the standard deviation of the x values, that R is this. So that formula actually isn't easy. They've just simplified R down to R rather than writing all that garbage. So if you're actually doing this by hand, it is horrible. Because if you think about what you have to do, not only do you have to do that terrible calculation for R, but you need to find some standard deviations too. Right. The B sub 0 can only be found if you know B sub 1, which is why we always find B sub 1 before B sub 0. because b sub 1 is used in the calculation for b sub 0. We're going to round to 3 digits when we're asked for these things. Okay? There is no rule, but rounding to 3 will work for most situations. All right, let's take a look at an example. Okay? Here is the data set for 9 students, and it is the number of hours they spent studying, that's X, and their exam scores, that's Y. And we are going to run this test from start to finish. That is, we are going to test first that there is, to see if there is a correlation. And then, if it is a significant correlation, we'll then try to use the equation that we get to predict some scores from some hours of studying. Okay? All right, so in order to do this, the first thing we need to do is we need to get that data into the calculator so we can run our test. Okay? So our claim is, okay, studying more hours will increase the scores on the exam. So the claim is that there is a positive linear correlation. And how did I get that more hours will increase the score on the exam to be a positive correlation? Well, the statement study more, increase the score means that the graph should do this, right? If this is hours and this is score, it should go up, and that would mean a positive correlation. So then our hypotheses are null and our alternate. Our alternate will be that rho is positive. Our null will be that rho is not positive, essentially 0 or negative. Right? Our data is that table up there, and also an alpha level of 0.02. Right? All right, let's get that data in the calculator. I'll be right back with that data in the calculator. All right, I've got the data in the calculator. Remember, I still have that stat plot turned on since I didn't turn it off. So all I have to zoom is to a stat window, zoom 9. And what's that? Oh, let's clear that out of there. Yeah, that data doesn't look too bad. It looks pretty linear, so let's run the test. So stat, test, linreg t-test. X's are in list 1, that's good. Y's are in list 2. Frequency is a 1. My alternate is greater than 0, so that's good. I'm storing the equation in y1, that's good. And I'll go ahead and calculate. My test statistic, should I need it, is that 10.28. My p-value, holy cow, look at that. Look at that p-value. Is 8.8988, whatever, times 10 to the negative 6. So that's 5 zeros and a 9, because that would round to 9. When I compare p to alpha, p is way less than alpha. So we're going to reject the null hypothesis. I'm rejecting the null hypothesis, but the claim is the alternate. So that means that there is enough or sufficient evidence to support the claim. But that's not really what we're supposed to do here. I mean, we are doing that, but what we really need is, now that we know that the evidence supports the claim that there is a positive linear correlation, what's the equation? Now, here's another problem that we're going to have. It's a nomenclature issue. I'm looking for y hat equals b sub 0 plus b sub 1 times x. The good people at TI decided not to use that notation. They're using y equals a plus bx, where the a is the b sub 0 and the b is the b sub 1. So when I look at the calculator screen over there and I see that at the bottom there, do you see where it says a and b? So when a calculator tells me that A is 37.449, I know that's the B sub 0 in the stats world. And when I look over at the calculator and I see that it tells me that B is 7.451, I know that that's the B sub 1 in the stats world. So my regression equation, when I put it all together, my regression equation that has been shown to be statistically significant is going to be y hat equals 37.449 plus 7.451x, where y hat is going to be the predicted score and x is going to be the number of hours that they study. So now to answer these three questions right here, essentially what they're asking me to do is, what would be the predicted score if they studied for 3 hours? So plug in a 3 for x and see what happens. What would be the predicted score if they studied for 4.5 hours? So plug in 4.5 for x and see what happens. And then 10 hours, just plug in 10. So I can do that. I can go over here and say, what's 37.449 plus 7.451 times 3? And that's plugging in the 3. And I would get that y hat of 3 would be a 59.802. So if they study for 3 hours, their predicted score would be 59.302. Well, what if they study for 4.5 hours? What would be y hat of 4.5? Well, 37.449 plus 7.451 times 4.5. And I would get that their predicted score would be 70.9785, and round wherever they would tell me to round it. Probably 3, since everything else is 3, so maybe 978.978. Or maybe they would want, since all of the data is just to the ones, maybe they would want us to call this guy up here 60, and then maybe we would call this one 71, just wherever they would tell me to round it. The last one would be y hat if they study for 10 hours, y hat of 10. So let's see, 37.449 plus 7.451 times 10. And I get 112. All right. Now, we have just shown a problem, an issue with this. All right. I feel pretty comfortable with this statement, and I feel pretty comfortable with this statement because those are values that are within my data set. I feel pretty good about 3 and 4.5 because I've got data below 3 and above 3. I've got data below 4.5. I've got data above 4.5. The technical name for these two right here, is interpolation. You are interpolating, or you have interpolation when you use your regression equation to make predictions within the data set. Right? This guy down here, that's extrapolation. Extrapolation is when you use your equation to predict outside of your data set. Now, interpolation is generally considered safe because you have data above it and below it, and the equation probably models it really, really well. Extrapolation is sometimes scary, and this is an example where it's scary. Now, I'm assuming that essentially these are scores on an exam, but these are like percentage scores on the exam, and that somehow the student's going to get 112% on the exam. And I just don't see that as possible. So we're running into one of the problems that exists in statistics. I can find an equation. I can show that there is statistical evidence to support finding the equation. But just because I can find the equation doesn't mean I can throw whatever number into it I want. Interpolation is good. Extrapolation is dangerous. If you go too far outside your data set, it can be quite dangerous. Our data set goes from 0 to 8 for the x's. Going to 10 is going 25% outside that data set. So going 25% outside the data set, clearly here, gives me an issue. I can't get 112 on the exam. I can only get a maximum of 100. So I don't know that I would trust this as a result. Now, if you're wondering, how far outside of a data set can you go before it turns from an okay thing to do to a bad thing to do? You need about 3 more stats courses to get to the point where you would have enough math under your belt that you could measure that. There's ways to do it outside the scope of this course. What we should take away is, in general, interpolation is safe. Extrapolation, you don't want to go too far outside the data set. Right? If my data set has a range of 8, I don't want to go more than 1 or so outside the data set. And if I do go outside my data set and my equation gives me a wonky answer, 112%, can't do that, I should accept that that's not a reality, and that's a bad prediction going on there. Okay? All right, so when we're making our predictions here, when we're using our regression equations to predict the value of one of the variables, so regression equations predict value of one variable, okay, we should consider the following. Right? Sometimes our model can be bad. Right? If it doesn't look like it should be used, don't use it. Right? If it's not linear, don't use it linear just because you can. No matter how much garbage data I put in, the calculator can find a linear regression, but we shouldn't use it. If you got a bad model, the best predictor is just the sample mean. That's the best thing you can do. I have nonlinear, I have garbage data. The sample mean for the y values is the best that you can give for a prediction. If you have a good model, like what we had in the last one, you can use it for making predictions, right? But you need to be careful that you don't extrapolate too far. Because if you extrapolate too far, you can get wonky answers that, if you think about them for a second, no way that could make sense. Right? Correlation, only do that regression equation when the correlation tells you should. Right? And then scope, and this is that idea of interpolation and extrapolation. Right? Only use the regression line. Don't go too much beyond the scope of the available data. So our data, remember, was 0 to 8. Right? We tried to use it for 10, and it looks like 10 was just too far outside the data set. Right? Now I want to point out something back up here. Right? All of these examples I did were give me an X, find me a Y hat. Could we turn that around? Could we take a Y hat and work backwards to find an X? Like, let's say that I wanted to get an 85 on the exam. Could I put an 85 in for Y hat and then solve for X to know how many hours to study? And the algebra doesn't care. It just says if you know one variable, you can find the other. So we definitely could. So all of our examples here, while they were, here's an X, find a Y, you can definitely turn this problem on the head and say, here's a Y, find me an X. Here's a Y hat, a predicted value, find me an X. Okay. Just some other things. Marginal change. Of course, it's stats, so we can't call it slope. No, slope is a, what is it? Slope is a math term. This is stats. So we have to call it the marginal change. Right? So if someone were to come to you and say, according to your data for the exam scores, what is the marginal change? So you'd look at it and go, okay, marginal change is the slope. That's that guy. So the marginal changes for every hour of studying, their score will increase by 7.451%. It's the slope, but it's stats. So just like the B sub 0 and the B sub 1 and rearranging the order of the terms, I also give slope a fancy name. I call it the marginal change. So you see a question or someone asks you about marginal change, it's just a fancy way of saying the slope in the regression equation. Okay? Remember, outliers can be a problem, so keep an eye out for them. Okay? But again, you ready? It's stats. So we don't call them outliers. We call them influential points. Influential points are points that strongly affect the graph of that regression line. They strongly affect that equation for that regression equation. Outliers are influential points. Influential points are outliers. It's the fancy stats way of saying it. All right, I want to go back and look at something. Remember when we did this test and I said, put that Y1 here? Okay. After I ran the test, if I go back to my Y editor, do you see how it put the equation into Y1? And now if I were to look at the graph, it not only graphs the scatter plot, but it also throws that line on there too. So if I wanted to see it, if I wanted to see the data and the line graphed together, I can do that. I can just put that equation in there. I could even then trace and trace to 3, trace, switch to the line by pushing up, type in a 3, and it'll tell me that 59.8 that our score was. Now you might be wondering why. When I did 3 here, I got 59.802, and when I do 3 on my calculator, I get 59.803. It's because when the calculator put it in, did it round this to 3 decimal places? So if I were to go in there and delete out those extras and just round it, to 3, and if I were to round the slope to just 3, I swear sometimes my fat fingers make me crazy. And then go back to the graph and go back to trace and go to 3. There's my 59.802. And then go to 4.5. And there's my 70.9785. And then go to 10. Invalid. What's that? Oh. When I zoomed, see how the window only goes to 8.8? If I try to type in a 10, I'm going outside my window. So I changed that a little bit to like 11, go back to the graph, go to trace, go to the line. Now I could go to 10 and I could get that 111.95, which we call 12. So this is just another way that you could evaluate or predict Y hats from X's. Okay? I don't recommend it as a way to do it, just because especially with that last issue with changing the window. But some people like to do everything on the calculator with the calculator, and it does do that. Right? So it's just another way you could do it. All right, I want to change something here real quick. So follow with me. Let's see, I need to make this L5. And I need to make this L6. This is the Yellowstone data about Old Faithful. And if I do clear this, if I do a zoom 9, that's that Yellowstone data. Stat, test, linreg t-test. Calculate. There's the equation of the line. And if I graph it, there's the equation of the line on top of the data. So now I've got an equation that I could use to predict the time interval between eruptions if I knew how long an eruption lasted. So now, next time I go to Yellowstone, which I think I'm going this summer, if I go to Old Faithful and I get my stopwatch out and measure how long it takes for the eruption to happen, I can use that equation to predict how long it's going to take before it erupts again, so I'll know if I have time to go get a soda or not. I'm so excited that I can put this into application because I love statistics. I think it's fascinating. Okay. That brings us to the end of section 10.2. I'm hoping that it made sense to you. If you have any questions, as always, please reach out. Have a great day.